If we look at homework set number 1, problem 2, the equivalent reluctance part, that's fairly straightforward. So I'm going to assume that we have all done that part correctly. Let's see here. Homework number 1.2. The answer to part A was provided to you. You had an equivalent reluctance of 9.24 times 10 to the 3 amp turns per Weber. Part B is fairly straightforward. That's not the part that I'm getting asked questions about. Part C is the bit that I'm getting asked questions about. In part C, you are asked to determine the amount of coil current I needed to generate a magnetic flux density of B is equal to 0.1 Tesla in the leftmost leg of the core. So I'm not going to draw the core per se, but I am going to draw the equivalent magnetic circuit. So this is the reluctance of the left leg in its entirety. This is the reluctance of the right leg, excuse me, the middle leg in its entirety. And over here, we have the reluctance of the right leg. And it's effectively in series with our MMF source, where our MMF is just N times I. And I is the coil current that we're actually looking for, okay? We are given the amount of magnetic flux density B that's flowing in the leftmost leg. And we can use that piece of information to determine this flux, which I'm going to call phi left, where phi left is simply the magnetic flux density flowing through the left leg times the cross-sectional area of the left leg, which looks to be 10 centimeters times 8 centimeters, so 80 centimeters squared, right? That's an easy enough calculation. And so the question that I've been getting is, how do I use the information that I've been given to find this current I, right? So one of the great things about magnetic circuits is that they behave pretty much identically to electrical circuits. So what I am going to do is use current division backwards, because our flux is playing the role of current in these magnetic circuits. So I believe that if I know what that flux phi left is, I can in turn then figure out what our coil flux is. And once I know the coil flux, I can use effectively Ohm's law for magnetic circuits to solve for the current I, okay? So do any of you guys remember how current division works? So we can do it that way, sure. So since we only have 2 parallel branches that we're dealing with, we can definitely use the resistance of the opposite leg, or in this case, the reluctance of the opposite leg, to give us the relationship that we're looking for. So we would say that phi left is equal to phi coil, right? Because the coil current's the thing that's splitting up. So we're finding this equation is effectively going to be like finding how much of the coil current splits to give us the left current. And then we're going to work backwards to figure out the things. Times the reluctance of the middle branch, which is the branch we don't want the flux through, divided by R left plus R mid. And turning this guy around, we can then say that our coil flux is phi left times the reluctance of the left branch plus the reluctance of the middle branch divided by the reluctance of the middle branch, right? So that gave us our coil flux. Now, using Ohm's law for magnetic circuits, which is our voltage, so our MMF NI is equal to our current or our flux times our reluctance, we can rearrange this guy and find that our coil current I is equal to our coil flux multiplied by our equivalent reluctance divided by the number of turns. So that's one of a couple of different ways I can think of in order for you guys to get the coil current. To me, that's probably the most efficient way, but it may not be the most straightforward way to do it. Another way that you could potentially do things, and I'm not going to go into a super detail here, is you also use voltage division to find this MMF and use effectively voltage division. The flux phi left times the reluctance R left will give us the MMF drop across that parallel combination. And then you could use voltage division backwards to also find the MMF of the source and then divide that MMF by N to give you the coil current. That's a different way to do it. Roughly the same number of steps. It's just a slightly different way to think about things. A third way to potentially do it, for whatever floats your boat, using Ohm's law, we can find that MMF sub X. Knowing that MMF sub X, we could then find the flux through the middle branch, just using effectively Ohm's law. Kirchhoff's current law with fluxes would allow us to calculate our coil flux, and then we could use our coil flux to find I. So much like an electric circuit, there's always 8 different ways to do anything with any of these. It's just whatever you're most comfortable with. I showed you the way that I choose to do it because it gets it all done in 1 to 2 steps. You'll use a very similar relationship that we did, like we did here, for parts C and D of problem 3 as well. I did happen to notice that I made the same simple mistake on problem 3 as I did on problem 2, calculating the equivalent reluctance. So I have since gone back and updated the assignment sheet yet again to give you the right answers for equivalent reluctance and everything from there on problem 3. Because of my mistakes and because it seems like you guys need a little bit more time to solve for the currents, I'm going to push the due date of homework set number 1 back until tomorrow. So you'll just have one more day to wrap things up. If you've already submitted your assignment and need to go back and correct some mistakes, just correct the mistakes and submit a new one. That's why there are 3 different options. And I'll just make sure that the grader only grades the most recent submission. So there should be opportunities for you to fix things since the due date got pushed up. All right. Any questions before we talk about what I actually wanted to talk about today? Walk through it. Let me look at it really quickly. So open homework set number 3. My short answer is unless it's significantly different, no. Oh, it's not a PDF file. That's why I can't find it. Let me open it up in Word or whatever. Open the folder. Go to problem 3. So it's effectively the same generic thing, except that this time you were given the flux. Can I draw on this? Probably. Let's see what this sparkly pen thing does. So you were given this flux phi sub g. That's, we can assume that it's flowing down through here. There's got to be a way to get a finer point on this thing. Oh, I'm not going to use it so much. So let me think about things. Assuming that you found the equivalent reluctance and all of that kind of jazz, you're given phi sub g, which is the flux through the gap, and that's the same flux that's going to be flowing through that total middle path. You're trying to find the coil current I, so it's still that current division backwards kind of thing. So you would find this flux by coil. The pretty space thing is starting to annoy me, so I'm just going to change to a normal color. And then once you found your coil flux, you could solve for the current I again. Yeah. Yep. Has to be, we're assuming we're not losing anything really. Yeah. So whatever flux is flowing through the air gap is the same amount of flux that's flowing through that middle branch. And then from there, it's literally the same relationship. Anything else? All righty. Let's just go to a new page here. All right, so today we are going to very loosely begin our talk about transformers. And by that, I mean, we're not going to really mention the concept of transformers at all. We're just going to build up to it. Oops, that's the wrong color. So what we're actually going to be talking about today is the concept of flux linkage and inductance. So in our last class meeting, I mentioned Faraday's law of electromagnetic induction to you guys when I was explaining what eddy currents were and how they came from, right? So Faraday's law of induction is just a equation effectively that tells us how a time varying magnetic flux causes induced voltages and currents in conductors. Mathematically, Faraday's law of induction is given as follows. So we have an EMF that is induced, where EMF is just a fancy term for voltage. I believe I've told you that before. So our induced voltage is going to be equal to the closed line integral of our electric field dotted into some differential line element, where that's literally just our definition of voltage. So I'm just going to put this down here. This part represents some induced voltage. And this is equal to negative the time derivative of the integral, it's a surface integral, of B dotted into dA. So what is B dotted into dA represent? That's magnetic flux. So expressed in a different way, we could say that our induced voltage is equal to negative n. And I'm pulling this n effectively outside of the derivative because it's a constant, where n is our terms ratio times the derivative of our magnetic flux with respect to time. And this is often expressed as the derivative of lambda as a function of time with respect to time, where this quantity lambda is simply equal to the number of turns times the magnetic flux that's passing through the turns of our coil. And it's what's known as our flux linkage. Something that we talked about briefly in 280 or whatever class it was that you guys had with me before, when we were talking about the concepts of self-inductance and mutual inductance. That's literally all we're going to do today. We're just doing it in terms of magnetic circuits as opposed to normal circuits. So we can really see where those relationships come from. The electric circuit representation is actually a side effect of what's going on in the magnetic circuits. So, all right, so the flux linkage of a coil is related to self-inductance using the following relationship, right? So our flux linkage, lambda, is L self-inductance times our current, right? So this L here is the self-inductance measured in henries. And this I of t is the time varying current creating our flux phi of t. So another way to think about this is that inductance L is the flux linkage divided by the current that's generating the flux. Using this particular relationship, we can substitute back in N times phi B over I, and using Ohm's law for magnetic circuits, we could express phi B as N times I over R. So this is going to be N over I of t multiplied by N I over our reluctance. And we can see very easily then that our i's cancel each other out, and we're left with N squared over R as our equation for self-inductance in a magnetic circuit, right? So as long as we know what the turns ratio is and what our equivalent reluctance is, we can determine inductance. So let's use this relationship to determine the inductance of the following magnetic circuit under two specific conditions. So let's say that I have the following core shape. It's going to be a horseshoe-like core with an air gap, and we're going to see what role the air gap plays in determining inductance. So here is our core. We're going to wrap a wire around it. like so. We're explicitly saying that our current is time varying now. And that our coil has 500 turns. This distance is our core length. So I'm just giving you the whole length so that we don't have to suffer through adding together all of the little parts and all of that kind of stuff. So our core length in this case is going to be 30 centimeters. Our gap length, LG, is going to be 0.5 millimeter. To make our lives a little easier, we're going to go ahead and calculate the core area. So let's say that it's 3 centimeters by 3 centimeters, which is going to give us 9 centimeters squared. And our gap area would then be 3.05 centimeters quantity squared, or 9.3025 centimeters squared, where all I've done is just add the gap length in the width direction and add the gap length in the thickness direction, and then squaring ourselves. So let's say that our core is made of M5 steel, where we have a core permeability of 72,300 times mu naught when it carries a magnetic flux density of 1 Tesla. So this would be somewhere in the linear range of the BH curve. And then our core permeability is 2,900 mu naught at a magnetic flux density of 1.8 Tesla. So just so that you're catching what I'm throwing, if this is B and this is H, and this is our BH curve, our first point is somewhere down here, where we see that a very small change in the H field causes a very large change in the B field. So this is our first point. And then our second point, probably somewhere around here in the knee area. If we were to go into the saturation area, we would see that mu C would be even smaller, because we know that even a large change in the H field will result in a very small or almost no change in the B field. So what we are investigating here effectively is 2 things. A, what the impact of having an operating point on different parts of the BH curve is going to do to our inductance. And B, we're going to see what impact the reluctance of the air gap plays in these calculations as well. So let's start with our core reluctance at the 72,300 mu naught, right? We have the reluctance of our core, which is just going to be LC divided by mu C AC, or 30 centimeters over 72,300 times 4 pi times 10 to the minus 9 henries per centimeter times 9 centimeters squared. I got to be 3.669 times 10 to the 3 amp turns per Weber. we have our gap reluctance determined by LG divided by mu naught times AG. So that's going to look like 0.05 centimeters. Divided by 4 pi times 10 to the minus 9 henries per centimeter times our area 3.025 centimeters squared. So I get 4.277 times 10 to the 5 amp turns per Weber. And then my equivalent reluctance is just my core reluctance plus my gap reluctance, which comes out to be 4.314 times 10 to the 5 amp turns per Weber. Using this value, our self-inductance L is going to be N squared over REQ, or 500 turns squared, divided by our 4.314 times 10 to the 5 amp turns per Weber. And this comes out to be 579.522 millihenries. So a little bit more than half of a henry. Just for the sake of argument here, looking around at the units, turns are unitless quantities, so they're not really going to matter. So we wind up having Webers per ampere, where a Weber is a volt second, and a volt second per ampere is a henry. So we have a self-inductance of 579.5 millihenries at this very, very high core permeability. Okay. Now we're going to solve the exact same relationships using mu C is equal to 2900 mu naught. So that's a reduction in our core permeability of a factor of roughly 25. So 25 times smaller permeability. So for mu C is equal to 2900 mu naught, we find that RC, I'm going to skip the equations and all of that kind of stuff because it's literally the exact same equation. We wind up getting 9.147 times 10 to the 4 amp turns per Weber. Our gap reluctance literally does not change, 4.277 times 10 to the 5 amp turns per Weber. Adding these guys together, we get 5.192 times 10 to the 5 amp turns per Weber. And then we get our self-inductance N squared over REQ. In this case, comes out to be 481.520 millihenries. So this is an interesting thing, right? I say it's interesting because, as I mentioned previously, our core permeability reduced by a factor of almost 2,500%, right? Roughly 25 times smaller. Did our self-inductance change by a factor of 2,500%? Not even close, changed by 16%. So the purpose of an air gap from the perspective of an inductor is to kind of linearize it and make sure that it doesn't change too much, even when we're magnetizing the core material at very, very different strengths. Okay, so the air gap, it doesn't make the self-inductance constant, but it makes it not be able to change by a large amount. All right, so we've talked about self-inductance. Now let's make things wildly more difficult and talk about mutual inductance. So I'm going to draw a core material here. I'm going to be a real jerk about things and introduce a second coil. So here's our core material. We just have a simple rectangular core. Now I'm going to wrap a wire around this guy. Because we're dealing with more than one coil, we're going to have to pay attention to the directions of the windings here. So our first coil has N1 number of turns, and it's carrying a current of I1. And then our second coil will be over here on this right-hand leg. Like so. It'll be carrying a current of I2, and it has number of turns of N2. So let me ask you guys what I hope to be a simple question. What is the direction of the flux that's generated by our first coil? Up, right? So using the right-hand rule, our fingers wrap around in the direction of the winding. Our thumb gives us the direction of the magnetic flux. So we're going to have a flux going in this direction. I'm going to call this flux phi 1 of t. Because our current is time varying, our magnetic flux will also be time varying. What direction is the flux traveling in that's generated by coil 2? Down. Absolutely right. So we now have two fluxes traveling around our circuit. And in this particular case, they're both traveling in the same direction, which is going to make our life a little bit easier because everything's going to have positive signs. So if I were to represent this as a magnetic circuit, it would look something like this. I would have my MMF1, which is simply the number of turns in coil 1 times the current being carried by coil 1. Here I have my equivalent reluctance of my core. And over here I have my second MMF, MMF2. Simply the number of turns in the second coil multiplied by the current flowing in the second coil. Like so. And I can indicate my fluxes as follows. So here's phi 1. And here's phi 2. So what is the flux linkage of coil number 1? So my subscript 1 there is telling me that I'm interested in what's going on with coil number 1. So if we go back a couple of pages in our notes, we can see that flux linkage is nothing more than the number of turns times the flux passing through the coil. So the number of turns of coil number 1 is N1. And then we have some total amount of flux that's passing through our magnetic circuit. Okay. In our case, where our coils are wound in effectively opposite directions, this is going to look like N1 times flux generated by coil 1 plus the magnetic flux generated by coil 2. So what is the magnetic flux generated by coil number one? So imagine that coil number two wasn't even in the circuit. It was turned off or it wasn't carrying any current, right? What would our magnetic flux from MMF1 look like? Just use Ohm's law for magnetic circuits, right? So we would have Ni divided by the equivalent reluctance. Okay? So since we're dealing with coil one, that's going to look like N1 I1 divided by the equivalent reluctance seen by coil one, which is just the equivalent reluctance of this particular core. And the flux of coil two is simply going to be N2 I2 divided by that same equivalent reluctance. Now I can lump some things together. So I have N1 times N1, so that's going to be N1 squared divided by our equivalent reluctance times the current I1 plus N1 N2 divided by our equivalent reluctance times I2. What does N1 squared over reluctance look like? Yeah, so that's our self-inductance, okay? So I'm just going to call this L11, and I'll tell you how to read those subscripts in just a moment, but it's just the self-inductance term. And then N1 times N2 over reluctance, that looks like an inductance, but it's not just for the single coil. So that's the mutual inductance seen between the two different coils. So let's call this M21 times I2, right? So this L11 is our self-inductance term, and it is the flux generated by coil one that is passing through coil one. And then this M21 term is our mutual inductance term. And it arises because there is flux generated by coil two passing through coil one. So we're going to be dealing with subscripts a little bit here now. Let me make that 2 look more like a 2. And so the first subscript is where the flux is coming from. And the second subscript is what the flux is flowing through. So that's the convention that we're going to use for this particular class. So we could do a very similar derivation for the flux linkage for coil two, and we would find out that we would get almost an identical relationship, except that instead of having this L11 term or N1 squared over equivalent reluctance, we would wind up having N2 squared over the equivalent reluctance, which would be the self-inductance of our second coil. But our mutual inductance term would literally be exactly the same, right? Meaning that the mutual inductance of flux generated by coil two passing through coil one is exactly identical to the mutual inductance caused by flux generated by coil one passing through coil two. So it doesn't matter which coil is originating our flux and which coil it's passing through, the mutual inductance terms are always going to be identical. And we can use that to our advantage in analysis of these systems, which we'll do here in just a moment. So This derivation thing was fairly straightforward. Now let's look at a rather complicated magnetic circuit and see if we can determine self-inductance and mutual inductance of the various coils. So I am going to work out several parts of this problem. And then for your in-class assignment, I'm asking you to solve for literally one thing. So this is what our core structure looks like. Let me define some dimensions. So this is going to be length L1. This will be length L2, where L1 is 60 centimeters. L2 is 40 centimeters. This length right here is our gap length, LG, where LG is given as 1 centimeter. This is the width of our core material. Where our width is given to be 5 centimeters. Our thickness, the direction into the page, is also 5 centimeters. And let's say that our core's permeability is 5,000 E0. Now I'm going to wrap some coils around this guy. So let's put my first coil here. Like so. Let's say that coil A has 100 turns. And here's our current IA. Let's put coil 2 down here. Or coil B, excuse me. So let's call this NB, here's the current of IB, where NB is 200 turns. And let's give ourselves a third coil to worry about down here. And C, here's our current IC. And our third coil has 500. I want us to find the self-inductance of coil A, the self-inductance of coil B, the self-inductance of coil C, and then the mutual inductance seen between coils A and B. And then for your in-class assignment, I believe I'm asking you to find the mutual inductance seen between coils C and B. All right. So to determine our self-inductances, we are going to need to determine the equivalent reluctance seen by each coil. And because of this particular configuration, each coil is going to see a different reluctance. Okay. So making this look like a simple magnetic circuit, we're going to have something like this, right? So here is the reluctance that I'm going to call R sub L. It'll be in series with the MMF of coil B. Then I have my bottom left branch. Up here, I'm going to have my top left branch. In the middle, I'm going to have some reluctance. Let's call it R sub M. I have coil A's MMF. And then in series with that, I'm going to have the reluctance of my air gap. On the right-hand side, this is going to be the reluctance of my top right portion, the reluctance of that right vertical beam, my MMF for coil C, and then the reluctance of my bottom right. Can anybody tell me why I chose to draw the MMF for coil C positive polarity on bottom? So we can see by our windings that this coil is generating a flux in this direction, and this coil is generating a flux in this direction. And so I'm assuming kind of that my magnetic flux is leaving the positive polarity terminal of my MMF. And then this guy right here, for what it's worth, is driving our flux phi A around in this particular direction. Yes, they are. Since they're all in series, no. Right, and so like realistically, my coil for my coil B physically somewhere down here, but I'm just choosing to draw it over where it is because it's more convenient. Right, I could draw it on this bottom thing like this, but I don't want to for whatever reason. Exactly right. So as long as they're in series, I can move them around any way that I want for any of these six. Absolutely correct. Okay. So let's suffer through the boring stuff and calculate some reluctances really quickly. So the reluctance of my top left branch is going to be the same thing as the reluctance of my top right, which is the same thing as the reluctance of my bottom left, and the same thing as the reluctance of my bottom right. So all of those are identical because they all have the same cross-sectional area, they're all made of the same material, and they're all of the same length, right? So my top left reluctance will be, what's the length? Yeah, so half of L1 minus W, where that half gets distributed to both things, right? So half of L1 would be from here to here, and then we cut off this little bit right here, which is a half of W, and so we get half of L1 minus W. This is divided by the permeability of the core, UC, as well as the area of the core, which is just going to be the width times the thickness. And because we've done this calculation 800 times, I'm not going to put numbers in. I'm just going to hit you guys with what the answer is. I got 1.751 times 10 to the 4 amp turns per Weber. we can hopefully pretty easily see that our reluctance R sub L will equal to our reluctance R sub R. And R sub L, so what's our length for the the vertical beams on the left and the right side of our floor? L2 minus W, absolutely right. Divided by UC times the width times the thickness. And numerically, I got 2.228 times 10 to the 4 amp turns per Weber here. So I think the only things that we're missing are the middle. So what's the length of the flux path through that middle leg? Absolutely right. L2 minus LG minus W divided by UC times the width times the thickness. This came out to be 2.165 times 10 to the 4 amp turns per Weber. And then finally, the reluctance of the gap. Actually, I just have it as G. Is LG, that is definitely a Q, over U naught, sorry, times W plus LG times T plus LG. And that comes out to be 2.210 times 10 to the 6 amp turns per Weber. Simplifying things here then, just really quickly, I could say that my left leg is the top left plus the left plus the bottom left. This comes out to be 5.411 times 10 to the 4 amp turns per Weber. The middle flux path in total is R sub M plus R sub G, which comes out to be 2.232 times 10 to the 6 amp turns per Weber. And the reluctance of my rightmost path is going to be the same thing as the reluctance of my left path, 5.411 times 10 to the 4 amp turns per Weber. Are we all okay with that? All right, so redrawing this thing, we have something like this, right? So here's the reluctance of the total left-hand path with our MMF B in parallel with the reluctance of our middle path in series with MMF A in parallel with the reluctance of our right-hand path in series with MMF C. So my question to you guys, that R looks terrible. Is what's the equivalent reluctance seen by coil A going to look like? So we're calculating equivalent reluctance. So effectively, if we're finding the reluctance seen by A, we turn B and C off, so they look like short circuits. So what will we see? What's that? Which one's in parallel? All three? So just to be clear, A is the one in the middle. Yeah. So you were doing the right process, but you got it a little wonkified, right? So it'll be R mid in series with left and right in parallel, which is going to be the same thing as half of R left, because R left and R right are the same value. So that comes out to be 2.261 times 10 to the 6 amp turns per Weber. The equivalent reluctance seen by coil B is what Caitlin suggested, to where it's going to be left in series with middle in parallel with right. Because the middle and the right don't have the same value, I can't just say it's half of R mid or half of R right, so I'll have to do this out a little bit more explicitly. So R left plus R mid times R right over R mid plus R right, where I'm using the shorthand notation for resistances in parallel, because I don't like using that 1 over crap for the motor. And it's only two. Numerically, this comes out to be 1.132 times 10 to the 5 amp turns per Weber. And it should not be a huge leap to say that the equivalent reluctance seen by coil C is the same thing as the equivalent reluctance seen by coil B. Or 1.132 times 10 to the 5 amp turns per Weber. All right, so now that we've gotten through all of the same crap that we've been doing for the last 3 days at this point, I want you guys' input. How do I find the self-inductance of coil A? Yep, the number of turns squared divided by the equivalent reluctance seen by coil A, which comes out to be 4.423 millihenries. Very similarly, the self-inductance of coil B will be the number of turns in coil B squared divided by REQB. And that comes out to be 353.489 millihenries. So significantly larger self-inductance. Anybody care to venture a guess why? Yeah. So there are 200 turns in coil B, whereas there are only 100 turns in coil A. So because there are more turns, the inductance is going to be larger. The reluctance seen by coil B, 1.132 times 10 to the 5, is also smaller than the reluctance seen by coil A. So that's another reason that particular coil has a larger self-inductance. And then finally down here, we have LC is going to be NC squared over REQC. And this comes out to be 2.209 henries. And again, it's such an appreciable increase because of the number of turns, right? Coil C has 500 turns, whereas coil B only had 200. So when we square that, it winds up increasing our inductance by a whole hell of a lot. All right, so the easy part is done. This is really nothing more than you guys have already done, except that now we've introduced this new equation where it's just the number of turns squared divided by the reluctance, right? Mutual inductance is unfortunately going to be a little bit more complicated, okay? So in order to determine the mutual inductance between coils A and B, we either need to determine the magnetic flux passing through coil B caused by the MMF at coil A, or vice versa. So we have two different options, okay? So we have this magnetic circuit where we have our left reluctance our middle reluctance, and then here's MMF A, and then our right reluctance. And effectively what we're interested in finding would be this flux, phi AB. So just to be clear, how we're reading that is the flux generated by coil A that passes through coil B. Or we can look at this guy. So here's our left. Here's MMF B. Here's our mid. Here's our right. And we're trying to find this flux, which will be phi BA, again read as the magnetic flux generated by coil B that's passing through coil A. So we get to choose our own adventure here. For what it's worth. We will get the exact same result regardless of which one we choose. So we just choose the one that seems easiest to us. So which one seems easiest to you guys? The second one, okay. So finding the MMF that's passing, generated by coil B, that's passing through coil A. Yeah, so the second one, MMF or flux generated by B that's passing through coil A. Okay, so how are we going to determine that flux? We have several different options here. So the current division thing seems reasonable-ish, except for one small caveat. We don't know any flux anywhere. And to apply current division, we kind of need to know something. Now, realistically, we could make it work for us, right? So we could relate. So let me see how to put this. So this flux, let me do it in a different color here. Right here, this would be the flux that's generated by coil B that's passing through coil B. And we could use current division to figure that out, to figure out how phi BA relates to phi BB. And then we could use Ohm's law for magnetic circuits to figure out how phi BB relates to the MMFB. So that's definitely doable. You know what? In fact, let's do it that way because you guys suggested it and we won't worry about my way because we should get the same result either way. Okay. I'm using voltage division and Ohm's law, and this is going to use current division and Ohm's law, so it's roughly the same level of difficulty. It's just the steps are in a slightly different order, so I'm going to have to think about things instead of just writing down what I have already written down. That's okay. It's not bad to think every now and then. All right, so let's think our way through this, right? This may backfire spectacularly, and that'll be okay. So the flux phi BA that we're looking for is going to be the flux phi BB multiplied by the reluctance of the right-hand branch divided by the reluctance of the middle branch plus the reluctance of the right-hand branch. That is the flux that's generated by coil B that's passing through coil B, and I've indicated it on the figure above. So flux and inductance are different quantities. They're related to each other, but they're not the exact same thing, right? So now we need to figure out phi BB in terms of MMF, okay? So what's our relationship between MMF and flux? That's that Ohm's law for magnetic circuits relationship, right? So just doing it out here, I'm going to do it in a separate color. MMF B is going to equal to our flux phi BB times the equivalent reluctance seen by coil B using our Ohm's law style relationship, where MMF plays the role of voltage, flux plays the role of current, and reluctance plays the role of resistance. So to me, I'm reading this as effectively V is equal to IR so that I don't screw it up. Okay. So from here, we could then say that phi BB is just MMFB divided by REQB times R right divided by R mid plus R right. So let me think about this here really briefly because we're doing it slightly differently than how I had intended. So REQB you know what? Let's leave it like that. We have a numerical answer. Let's see if it shakes out the way that I expect it to. Okay. All right, so we have our flux. Our goal is to find our mutual inductance. So the flux linkage of coil A is going to be negative NA times phi BA, where the negative sign comes from the fact that the flux seen in coil A generated by coil B is opposite to the direction of the flux that's generated by coil A. So effectively, it would be positive if, just as a separate thing here, so I'll try to explain this better way. So this is the direction of the flux that's generated by coil A, right? It's in the up direction. Because phi BA is in the opposite direction, we get a negative sign for our flux linkage. That's literally as difficult as it needs to be, okay? So if the flux that's generated by coil A is up and phi BA is down, we get a negative sign. If we had reversed the windings of coil A so that the flux generated by coil A was down, we would have a positive mutual inductance thing. All right. So our mutual inductance, MBA, is going to be our flux linkage divided by our current. Well, our flux linkage we know to be negative NA over phi BA. Divide that by IB. And I'm going to move some things out here. So negative NA over IB. Now I'm going to substitute in MMF of coil B times R right divided by R mid plus R right. And then over here, I'm going to have 1 over REQB. The reason why I'm writing it in this way is because now we're going to replace that MMF from coil B, because that's not something that we actually know. We just know what things are that make it up. So MMFB is going to be IB times, hold on, NB times IB. So this bit right here can be replaced with NB times IB. And from that, this IB and this IB cancel each other out. We never knew the current, so now we got rid of something that we don't know. And we have everything expressed in terms of something that we do know, right? So ultimately we find that our mutual inductance is going to be negative NA times NB times R right divided by R mid plus R right times REQB. And now let's throw numbers in this thing and see what happens, which I hope it works out favorably for us. So let's go back here. So R mid was 2.232 times 10 to the 6. Amp turns per Weber. R right was 5.411. Times 10 to the 5. 10 to the 4 amp turns per Weber. REQB was 1.132 times 10 to the 5. Amp turns per Weber. In our numerator, we have NA, which was 100, NB, which was 200, and then R right, which was 5.411 times 10 to the 4 amp turns per Weber. And here's crossing our fingers that it comes out to the same result that I got previously. I didn't bring a calculator, so somebody tell me what, or somebody let me borrow a calculator, one or the other. Thank you, Avery. I will turn this moment. All right, so throwing this in my calculator, or Avery's calculator as it were. 100 times 200 times 5.411 times 10 to the 4 divided by 2.23232 times 10 to the 6th plus 5.411 times 10 to the 4. That quantity multiplied by 1.132 times 10 to the 5. $4.182 times 10 to the minus 3 henries. So not wildly far off from what I had gotten originally. I think it's a likely rounding error. So this seems to have worked out pretty okay. Just for the sake of argument, how I had worked it originally, let me get rid of this thing, was effectively using voltage division. So I found this MMF and then divided that MMF by the reluctance of the middle branch to find the flux flowing through that. So that MMF division thing there, just for the sake of argument, I'll do it down here, looked like MMF of X was the MMF of B multiplied by R mid in parallel with R right divided by R left plus R mid in parallel with R right. And then phi BA was just MMF of X divided by R mid. And then after that point, same steps. All right, so that's enough out of me for today. You've got 25 minutes to work on your in-class assignment where you're literally doing what I just did, except for finding the mutual inductance between B and C. So 80% of the work has been done previously. Now you're just applying that to figure out the last few things. So let me distribute this.